Okay, here we go. So section 3.4, second derivative test. There we go. So this first example represents all the different ways that we can draw a graph where the first derivative is positive. So the first way would be like this. So see, if we were to put like a little tangent line right here, that first derivative, that slope of that tangent line would be greater than 0. So that's one way we could do it. Another way that we could draw would be like this. Okay, different curve. Notice what's the difference? The concavity is what's different. But if you were to put like little tangent lines on here, their slopes would be positive. So it's still increasing. Okay. So just to like reiterate what I was talking about earlier, notice right here, I'll go like right here on this graph. The slope of that tangent line is positive. It's not as steep as this tangent line, but it's still positive. This one's definitely steeper. Right here, this is even steeper than both of those. So this graph is increasing at a rapid or fast rate. This graph, now this little tangent line right here is still positive. This one's still positive, but not quite as positive as that one, right? It's not quite as, not as dramatic. This one definitely not as much as these two. So this graph is also increasing, but it's increasing at a slower rate. So concave up increases rapidly. Concave down increases at a slower rate. And then the last one, which Mr. Corpy says is the boring one, is the linear function. And of course, this is also where the first derivative is going to be positive. Okay, so the tangent line is going to be the same slope all throughout that line. It's still going to be positive. It's not going to change. So if you were to take if you were to calculate the slope of this, it would be a constant. And then if you were to take the derivative of that slope, that would be the second derivative. Okay, so once again, hang with me here. So if I had a straight line and I were to calculate the first derivative of this straight line, that would be the slope of this. That slope is constant, meaning like everywhere you go on this line, the slope is the same thing, 2/1, whatever it is. It's going to be 2/1 everywhere. So the slope will be a constant. If I take the derivative of that slope, that would be the second derivative. Well, when you take the derivative of a constant, the derivative of a constant is 0, right? So that means the second derivative would be 0. So there would be 0 concavity for this, which makes sense, right? A straight line has like no curve to it whatsoever. It's just straight. So this is neither concave up nor concave down. It has no concavity because the second derivative equals 0. Okay? Hopefully that's like, that will make sense. If not, if you like go back and watch this again, hopefully it'll start to sink in. Okay? If you can grasp that concept in the beginning, like early on, it'll make everything else like just fall into place with regard to doing the steps of the process. Okay, you'll kind of get why your answer comes out to be whatever you get. Okay, so hopefully everybody's had a chance to draw these 3 pictures. That's really the basic idea of example number 1. Down here we have a little box. Okay. I would definitely jot the things down in this little box, or if you printed out these notes, I know some of you do that, highlight that box, make, draw attention to it so you remember. It goes over in a formal way what I talked about on the notebook paper that we had before we started. So f double prime, that's the second derivative. When the second derivative is positive, you are concave up. When the second derivative is negative, you are concave down. And then if it's equal to 0, what we just talked about, it's constant. It doesn't have to be like a positive. It can be, you can have like a positive straight line, positive slope, or a negative slope, doesn't matter. And then here's some visuals for you. I'll give you like a little bit to write these down. And when you're done writing down whatever you feel that you need, just give me like a thumbs up or a check mark so that way I know we're good to go to move on. All right, how are we doing here? Just about, oh, we got everybody. Nice. Okay, cool. So we'll keep moving on. And for example, number 2, this is also really nice way to, it looks like my marker kind of went through, didn't it? Let's see if I can like change colors. Okay, so if you can remember this circle, this will help you out, okay, with keeping it all straight. So right here, this first one, if the curve, like just focus on just that piece right there. If the curve looks like this, then that means your first derivative is positive. So you put a greater than sign there. So because your slope is positive, right? And your second derivative is going to be negative. Why is the second derivative negative? Well, it's because you are increasing at a slower rate, okay? So this is the situation in like, if you want to think physics, okay, or particle motion. This is the situation where the velocity is positive, but the acceleration is negative. So we're still moving in the positive direction, but we are not increasing at quite a very fast rate. Like we're accelerating less and less and less. So this would be the situation where the particle would be slowing down. Like we're still going somewhere, but not as fast of a rate. So it would make the particle slow down, okay? All right, now the other half over here. So this curve, if you had this piece, whoops, of the curve, well here, the slope of the curve is negative. So the first derivative would be negative. We're also concave down here. So this would also, the second derivative would also be negative, okay? So this would be as an application, this would be you have changed directions, you're going the opposite direction, and you're going faster and faster and faster in that opposite direction, okay? So this actually would be speeding up. This particle would be speeding up. It's kind of weird when they're both negative to like visualize what that is, but that's what's happening there. Okay, for the other half of the circle, so if we just look at this piece right here, this would be, let's see, if we just look at that piece. So here, your slope is negative. So your first derivative is negative. But your second derivative is positive. Okay? You are concave up and you have a negative slope. Okay? The last one, so this, once again, this piece right here would represent slowing down. And then this last piece over here in this corner, if you just look at that piece, only that piece, your first derivative, your slope is positive, and your second derivative is also positive. So you are positive slope and concave up. So in this particular application, your particle would be speeding up. They both have the same sign, so speeding up. When they have opposite signs, so you're slowing down. Okay, it's like those things are working against each other, so it makes the particle have to slow down. So that's a helpful visual. I would probably star that one as something if you are trying out flashcards this semester with your study tools or like Quizlet or something like that. I would use that to help study for sure. All right, so I'm going to move on. Here's another box that has a definition in it and also some really nice, I don't know if I can get all that. I think I can. Maybe I'll move this out of the way. Let me move this thing. You guys don't need that. I think I can move it. Yeah. No? Yes. Okay. So this is important. Okay. So we have this new vocabulary called an inflection value. Okay. Not reflection, but inflection. An inflection value is when a graph changes concavity. So it goes from concave up to concave down or vice versa, okay? So you've got some examples down in the bottom. The most common one is like if you have something like this and then it goes like that. So right here, you're concave down. And then there's a spot in the middle here. Somewhere in the middle, this curve decides to change its mind and go from concave down to concave up. That spot right there is called an inflection point or inflection value, either one. I guess to stick with consistency, I should say inflection value. I guess over down here, he actually says point. Okay. Either one, point, value, whatever you want to say. So that spot where a graph decides to change its concavity, that's an inflection point. Now, the one that I drew was nice and smooth and it like looked like it was so nice and gradual. Doesn't always have to be that way. You can have inflection values like the pictures down at the bottom of this set of notes. So you could, like, this is the one that I drew up above. This is the most common one. Or you could have something weird like this. You could have like this weird, like a piecewise function would do this to you, where you like get a little like pointy cusp right here, and then it changes like very dramatically from concave up to concave down. So maybe we should, so this is concave down. This is concave up. This one's concave down. Oh, I'm sorry. Darn. That one's concave up. This one is concave down. The last two pictures are examples of where you don't have an inflection, because this would be concave up, and this is also concave up. So even though the first derivative changed, notice the first derivative does change for that. Like this is a positive slope and this is a negative slope. You have a relative maximum. That like corner point right there would be a relative max, but as far as like an inflection point, you do not have an inflection point because we did not change concavity. And then this one, this one's concave down, and this one is concave up. Even though these changed, you don't actually have a point. It turned out to be a vertical asymptote. So that's a tricky one right there. You have to examine the domain of your function. You want to make sure that if you have a restricted domain, that you don't have that as like one of the restricted values is not one of your points of inflection, because if it's a vertical asymptote, there's no point there at all. So it can't be a point of inflection. Yeah, Juliana, question?
So wouldn't the third one also count as a cusp?
Yes, it would count as a cusp. Mm-hmm. So you would have a relative max there, and this would be where the first derivative doesn't exist. So that would be a critical value, because remember when we do our maxes and mins, you're doing critical values based off of where the first derivative equals 0 or where the first derivative doesn't exist. So this would be an example where the first derivative doesn't exist. So if the first derivative doesn't exist, I guess you could say the second derivative doesn't exist either, right? So that's another reason that a cusp is not going to, well, this particular one, I guess. Yeah, I guess we couldn't use, how would I say? It's like an exception to the rule, huh? This, you want to examine what's happening on either side of it. So like, since here, the second derivative is positive and here the second derivative is positive, that's really the reason that this is not a point of inflection. Because here you have a cusp. So the second derivative would not exist at this point either, but on either side of it, you have opposite concavity. So that's why this is allowed to be a point of inflection. So when we get into the rules on like the steps on how to do this, you're going to end up taking the second derivative and you're going to end up setting it equal to 0 like we did with the other ones with the first derivative. And you're also going to set it to where it doesn't exist. And these will still be the critical values for the second derivative test. So that's where, right there would be where the cusp example. Is that what you were trying to ask me?
Yeah, it's fine. I got it.
Okay. So when you're done writing all these down, go ahead and give me like a thumbs up or a check mark or something, so that way I know that I'm good to go to move on. You always do screenshots too, which maybe some of you are already doing. So that really, do a screenshot and then maybe insert it into like a doc or something, or I don't know, whatever works easiest for you. All right, cool. Okay, so moving right along, what we were just talking about is what is next. So the first thing you're going to do is try to find a possible inflection value. So remember, like sometimes, like what we had here, oops, what we had right here. So like sometimes it is an inflection value, sometimes the X value is not an inflection value. So you have to start out with a list of possibilities. That's what this is, possible inflection value. And it's shortcutted as a PIV in these notes. How do you find that? Well, you do like we just talked about. Set the second derivative equal to 0 and solve or figure out where the second derivative does not exist. That's going to give you a list of critical values. Some of them will be inflection points. Some of them won't, depending on how the graph behaves on either side. I'm going to just put all this on the screen. The theorems are basically saying in words what we're already talking about. The test, these 4 steps would be good to have. This first step right here helps you figure out domain restrictions. So what we're going to do is we're going to determine the domain to see if there's any like vertical asymptotes or jump discontinuities, that kind of stuff, or holes in the graph for that matter. And so that's step 1, figure out the domain. A lot of times they're just all real numbers, but sometimes you get one that has restrictions. Then you're going to take the derivative twice, set the second derivative equal to 0, solve. Also, figure out where the second derivative doesn't exist, if there is anywhere. Then we do a new number line, and we test points on either side of those critical values, those possible points of inflection. And then if it's positive and negative, we determine the concavity, and we can go on from there, okay? Where it's concave up, the second derivative will be positive, and where it's concave down, the second derivative will be negative, okay? And so all of this analyzing is to help you better understand how the graph behaves without being reliant on technology. Like this is all done. I don't have Desmos pulled up right now. All of this work that we can do with analyzing the first and second derivative will allow you to sketch a fairly accurate graph of any curve that you come across, any polynomial, and be able to like predict how it's going to behave, okay? And so the better that you understand that, the more like the farther you're going to be able to go with doing application problems and determining whether your answers are reasonable. You know, you get some crazy number on a test, you're like, no, that can't be right because I know the graph should be decreasing, that kind of thing, okay? That's why we're doing all this. Okay, let me know when you're ready for example 3. Give me like the check mark or the thumbs up whenever you're ready. I guess I can move this up just a little bit. Maybe up like this so you can take a look at. If you are done with writing stuff down, take a look at example 3 and just jot down. If you want to draw the graph, it's not too terrible, but think about what you would put down for letter A. What are all the possible inflection values? And then we'll go over it. Alrighty, so let's take a look. So you've got this like crazy looking graph. Remember the steps that you were just given up above? So the first thing you want to do is find any discontinuities of the graph. I see one discontinuity of the graph, and that's going to be at x equals h. You have a discontinuity that is called a removable discontinuity. So there's one. That was step number 1. I don't have any other discontinuities. Step 2, identify any possible inflection values in the domain by either setting the second derivative equal to 0 or finding where the second derivative does not exist. All right, so what we're going to do is look to see where the concavity changes, okay? That's how on a graph, that's the best way to figure out where the second derivative equals 0 or doesn't exist, okay? All right, so right here, this is an endpoint, so that's not going to be an inflection value. So all the way from here until about this spot right here, we are concave down. I guess we're still concave down right here, kind of weirdly drawn. And then right about, I guess we'll go with this dashed line, but right about here, we change from concave down to concave up, okay? So we would say x equals b is a possible inflection value. Now we're concave up and we're switching to, this is now concave down. So x equals c. This spot right here, the second derivative is not going to exist right here. In fact, the first derivative does not exist here. So this is a possible inflection point. So x equals d. Let's look at the concavity. So from this dashed line, like from D to E, we are concave up. E is another cusp. So the second derivative will not exist there. Here we are concave up again. At H, that was our point of discontinuity, so we listed that already. And then at K, we are concave, well, from H to K, I should say, we are concave down, okay? So K is not a possibility because that's an endpoint. A is also not an endpoint. Or I'm sorry, it is an endpoint. It's not an impossible inflection value. Okay. So there's all your possibilities to pick from. Now, letter B is asking you to determine which ones are inflection values. So it's the points where the concavity changes. So you're going to say at x equals, we'll do 8 or h at the very end. So at B, you're going to say yes, inflection, however you want to say that, inflection value. Okay, why? Because second derivative is, let's see, concave down. Concave down means the second derivative is negative and then goes to positive. Goes from concave down to concave up. So therefore it is an inflection value. X, okay, so I did that one. X equals C. So X equals C is right here. That is also yes. Inflection value. But now the reasoning is different. We're going from concave up. So second derivative is positive to concave down. So second derivative is negative. By writing this out, you would get full points on the AP exam. Your reader wants you to use derivatives to justify your answers, okay? So this is absolutely fine. Okay, did C. At X equals D. All right, so D, what do you think? That's a yes, right? So D is a yes. That's an inflection value. Why? Even though it's a cusp, still an inflection point. It's where the second derivative doesn't exist. But it's because we change from concave down, so second derivative is less than 0, to concave up. Got that? So at X equals E. All right, let's look at E. So at E, you have a cusp, but we go from concave up and we're still concave up. So that's a no, not an inflection point. You could say F prime does not change sign. Or if you want to be more detailed, you could say it stays concave up on either side of X equals E, however you want to explain that. All right, last one, X equals H. X equals H is a point of discontinuity. And what's happening, this is the question though, what's happening on either side of H? Well, we're concave up and we are concave down. So guess what? H is a yes. Okay. Now, the only reason we get away with this is because there actually is a dot that defines X equals H. If that dot was not there, like if this just didn't even exist, then we could not say X equals H because that X value does not exist in the domain of this function. But since they put that little dot right there, X equals H does exist in the domain. And since the second derivative changes from positive to negative, it satisfies the definition of inflection value. So that's a yes. Inflection value, and it's because the second derivative goes from positive to negative. Okay. Okay. Part C. List the open intervals on which the graph f of x is concave up, concave down, and or constant. So this is just listing intervals like very much like a pre-calc type question. So your intervals are going to be, let's see, let's do concave down over here and concave up over here. Okay, concave down looks like A to B in union with C to D. And then H to K. Remember, use parentheses, don't use brackets on the actual endpoints of those intervals. The graph is neither concave up nor concave down. So open intervals. Concave up is going to be from B to C in union with D to E. Yes, you do need to separate D to E and E to H, because at E, we are not concave up, we are a cusp. So separate that, D to E and E to H. All right. So stick with the definition and you can't go wrong. All right, it's going to be an inflection value as long as the second derivative or the concavity of the graph changes from positive to negative. All righty, any questions? Okie doke, moving on. So now we are on the back, another box. I would just take a screenshot of that box or highlight it, okay? So things to go over again. Not all points, not all inflection, not all possible inflection values end up being inflection values. Concavity can change at a discontinuity, but it's not going to be an inflection value like a vertical asymptote. That's a vertical asymptote can't be an inflection point because there's no point there. You're going to set the second derivative equal to 0, and then you're also going to find where the second derivative doesn't exist. That's how you're going to find those possible inflection points. And then you can create a chart that helps you stay organized with the concavity and figuring out where you're going to have possible inflection values, okay? Okay, so let's look at example number 4. I'll try to keep that box up there while we're like working these. So here's where you actually have the algebra to do and the derivatives that we've learned and solving. So for each of the following functions, find possible inflection values, the actual inflection values in state Y, and then do the intervals of the concavity, okay? So the first one we've got is Y equals 3 plus sine of X. We're on the interval from 0 to 2 pi. So we have an idea of what the sine graph looks like, has like that S. And then if you do 3 plus sine, that's just a transformation. It moves the whole sine graph up 3 units, right? So that's what we have going on here. We have a sine graph hanging out 3 units above where it normally would be. It is continuous. Sine is continuous. There's no discontinuities, and it's differentiable. So we're good to go here. So what we're going to do is take the first derivative, dy over dx. What will be the derivative of 3 plus sine x?
Cosine of x.
Yep, cosine of x. Good. All right, so that's the first derivative. We need to do second derivative for this. So now we're going to take the derivative again. The derivative of cosine x is
Negative sine x.
Yep, negative sine x. Okay. So negative sine x is also continuous. No discontinuities there. You're going to take that and set it equal to 0, and also decide if there's anywhere that that function doesn't exist on the interval from 0 to 2 pi. So we're going to say negative sine x equals 0. And then the other thing is negative sine x, like where it does not exist. Okay. Is there any place where negative sine of x would not exist? Like would there be a vertical asymptote or a hole on the interval from 0 to 2 pi?
No.
Right. So that part's done. We don't have to worry about that. The other part is this figuring out where it equals 0. So to get rid of the negative, you could just divide both sides by -1. And then now we have to think like unit circle time now. Where does the sign equal 0 on the interval from 0 to 2 pi? Closed interval, that is. What'd you say?
At 0, pi, and 2 pi.
Yeah, good. So at 0, pi, 2 pi, good. So these are your possible points of inflection, okay? Okay, so you make a number line, okay? And you're going to put 0, pi, and 2 pi. Okay. So this is where we have to remember like what our interval really means. So your interval is really only from 0 to 2 pi, right? So since I'm only working with 0 to 2 pi, I'm not going to be concerned with anything less than 0. I'm not going to be concerned with anything greater than 2 pi. Okay, so you really only need to test something in here and something in here. 0 and 2 pi just happened to be our critical values. And if you can picture a sine function in your mind, remember that just keeps going, right? Over and over again. We're looking for possible points of inflection. So they're going to end up on that. But we really don't have to test anything less than 0 or greater than 2 pi because of this restriction right here. So we should put something in between 0 and pi. How about pi over 2? Okay, so you put pi over 2 into the second derivative. Okay, so you're plugging these values in, plug into the second derivative. That's why they call this the second derivative test. You got to plug into the second derivative. Now, don't go back to this thing where we set equal to 0. That was just our algebra that we were doing. Go all the way back to that, your second derivative. So if we plug pi over 2 in here, because that's in between 0 and pi, if I plug pi over 2 in right here, am I going to get a positive answer or a negative answer?
Negative answer.
Yeah, good, negative, right. So what does that mean? That means that we are concave down. Your second derivative tells you about concavity. So if you get a negative answer, you are concave down. Okay, which should make sense, right? Think of that sine graph, right? Sine goes like this. Sine goes like this. So we should be concave down. All right, and then something between pi and 2 pi. How about 3 pi over 2? Convenient. If you plug 3 pi over 2 in right here, do you get a negative answer or a positive answer?
Positive.
Yeah, positive. So what does that mean? That means that you are concave up, okay? So we knew this because you've studied sine, you've taken a whole semester of trigonometry. So like, you know what the sine graph looks like. This is using the calculus to justify the reason that that curve is the way that it is, all right? So since the concavity of the graph changed from negative to positive, that means that x equals pi is an inflection value, okay? So when we got these answers over here, these were possible inflection values. The actual inflection value is at x equals pi because the second derivative changed from negative to positive. And take a few seconds to make sure that you understand that. Any questions about that? Okay, so the last part of this was, so we figured out the possible ones. We figured out the actual inflection value, which was at pi. Now the last thing is the intervals of concavity. So you are going to be, I don't know where I'm going to squeeze this, I guess up here. We are going to be concave down from 0 to pi. And you're going to be concave up from pi to 2 pi. Make sure that you are writing that as open intervals, no brackets. Okay, and that should make sense because at the very beginning of all of this, we talked about that the sine graph was going to look like this. So this is still pi right here. That's your point of inflection. Over here, this is 2 pi. So you are concave down, and then you change to concave up. So this spot right here is your point of inflection. All right, let's look at letter B. So for letter B, it's written nicely for us to take a derivative. I am going to rewrite it without the negative exponent so that we can think about like if there's any discontinuities, okay? So if I rewrite it like the positive exponent, that means this is all going to go down here. So we got to think about discontinuities. So like vertical asymptotes and stuff. The only place you'd get a vertical asymptote would be if that denominator equaled 0. So if you took x squared plus 3 and set it equal to 0, is there going to be an x value that's going to make that 0?
The square root of -3.
Yeah, right? So that would be square root of -3. And that becomes what? Imaginary, right? So thankfully, calculus does not use imaginary numbers. Calculus is based off of only the real numbers. So don't have to worry about that, okay? So no domain restrictions for this one. I wanted to make sure we talked about that though, because you have to see that process. If you were doing this on a test, that's what you would have to do. Set the denominator equal to 0. You get like an imaginary, then you're fine. You just throw it out. Okay, so now we're gonna start taking derivatives. So first derivative, f prime of x. I'm getting rid of all this. What would be the first derivative of that?
It would be -6 times x squared plus 3 to the -2 power times 2x.
Awesome. Thank you. All right. And so to make that a tiny bit easier to work with, let's, how about we multiply these two things? So how about -12x times x squared plus 3 to the -2? Right? I don't think I made any mistakes with that. Okay, so that was the first derivative. We need to keep going because this is second derivative test that we're learning here. So let's take the derivative again. Be super careful with this. What do we have to use with this? I guess.
Product rule.
Yeah, product rule, good. I guess if you really want to, you could change it and put the x squared plus 3 like down in the denominator and do quotient rule. Either one, you're gonna get like the same thing. So product rule means that this is gonna be u and this is v. So u prime would be -12 times v, so x squared plus 3 to the -2, plus, I gotta switch to notebook paper. This is just not enough space. All right, so f of x was 6x squared plus 3, -1. Okay. Oh, 100 times better. All right, so this is u and this is v. So second derivative, the derivative of u is -12 times v plus, now we're gonna do the derivative of v, which will be -2, so I'm going to bring this negative, make that be a negative, x squared plus 3 to the -3rd times 2x times, so that was just the derivative of v, all of this, times u, 12x. All right, that's beautiful. All right, so -12 x squared plus 3 to the -2. What can we do with this? Well, you got -2 times another 2 would be -4 times -12 would be +48. X times x, x squared times x squared plus 3 to the -3. Take a look at that and see if you agree. All right, so I think we're good. I have my other notes to see if I hope I didn't make a mistake. I don't think I made a mistake. All right. So
Where did the negative 12x come from?
where'd this negative 12x come from?
Mm-hmm.
All right, so you're gonna do u prime v plus v prime u. So all
Oh, I forgot to add u. Okay, okay, never mind. Yep.
Yeah. And that's easy to miss because this was the process right here. This was a lot to do just to get a derivative of one thing. So, yep. Okie doke. So now if I rewrite this, because remember, we're going to have to set it equal to 0. We're going to have to find where it doesn't exist, that kind of stuff. So we need to get it into like a fraction. So this would be negative 12 over x squared plus 3, quantity squared, like that, plus 48x squared all over x squared plus 3 cubed. So we should combine that into one fraction. So you need a common denominator, which is going to have to be the cubed one, x squared plus 3 cubed. So this, if I make this cubed, that means I need to multiply the top here by another x squared plus 3. Like, because I would have to multiply the bottom of this by another x squared plus 3. So that means I'd have to multiply the top. So this would be negative 12x squared minus 36 plus 48x squared. Okay, which when we combine like terms will be 36x squared, right? 36 minus 36 all over x squared plus 3 cubed. All right, I'll take a pause right there in case anybody has a question. Are we good so far? Is your hand cramping up from writing so fast? I wish you guys were in class. I know I probably say this once every like, I don't know how many days, but like usually this time of year, I have like an urn in my, like a coffee urn in my classroom, but instead I just have hot water and then I have styrofoam cups with like hot chocolate and marshmallows and stuff. And I can't do any of that this year and it really is a huge bummer. So I hope you're having a mug of hot cocoa at home on my behalf because it really stinks being here by myself. All right, are we good? The hot cocoa is for the students, by the way, not just me. Alrighty, so I'm not seeing anybody. Okay, good, thanks. Thanks for like the thumbs up and the check marks. Awesome, good. All right, cool. Those of you that don't have the thumbs up or the check mark, you have a question or like need more time? Okay, all right. Okay, so I'm not moving my paper, so I'm just gonna move it up just a tiny bit. So remember what we're doing here. This is the second derivative. You're gonna set this equal to 0, and you're also gonna find where it doesn't exist. So when you're doing that for a rational function, you take the numerator for the setting equal to 0 part, you take the numerator and set that equal to 0. And for the does not exist part, you take the denominator and set that equal to 0. Okay, and see what you end up with. So for this one, you can take a 36 out. So this would be x squared minus 1. Then you can divide by 36. So x squared minus 1 equals 0. It's okay if you want to add 1 and take the square root. Just make sure that you do plus or minus in front of your square root. I'm going to factor it because I notice it's a difference of 2 squares. And if you do that, you're guaranteed to get both your answers. Either way, you'll get it. So x equals -1 and x equals +1. Over here, where the derivative doesn't exist, we're back in that same situation as we were in the very beginning. You could cube root both sides. You get x squared plus 3 equals 0, and then you're back to x equals the square root of -3, which is imaginary. So we throw that out. Okay, so the second derivative is going to exist everywhere on this graph. So your possible points of inflection, your PIVs, are -1 and 1. So you make a number line, put -1 and 1 on there. I guess I need to make one of them negative. There we go. Put 1 and 1 on there. And then you need to check something smaller than -1, something in between 1 and -1, something bigger than 1, and see what kind of answers you get, positive or negative. Remember, you are plugging into the second derivative, which was 36x squared minus 36 all over x squared plus 3 cubed. Okay. Now, the goal here is to just figure out if it's going to be positive or negative. You don't need to know exactly what it comes out to be when you plug a number in, just whether or not it's going to be a positive number or a negative number. So I would start with, I don't know, whatever you want to pick, something smaller than -1. I would guess -2 might be a popular choice. So if you do -2 and you plug it in here and here, okay? I plug -2 in here. When you square -2, it's going to turn positive. And then you're going to so it'll be 4, right? And then you're going to multiply it by 36, which is going to be a number larger than this. So the top is going to be positive. When you put -2 in here, it'll turn positive. And then add 3, still positive. And then cube whatever that is also going to be positive. So positive divided by positive is positive. So I draw the little, I like to draw the concavity underneath just so that I can keep that thought in my mind. All right, now, if we want to do something between -1 and 1, how about 0? So 0, well, that's going to wipe this whole thing out. So -36, that's going to be negative on the top. And then if you put a 0 here, that's going to be 3. Cubed is also, that's going to be positive. So negative divided by positive is negative. You're going to be concave down. Okay, something bigger than 1. How about 2? So that's going to behave like when we put -2 in, because when you square 2, you're going to get the same answer as when you square -2. So this top is then going to end up being positive, and the bottom is going to be positive. So this is going to be positive, which means you're concave up. Okay. So our actual inflection values are going to be at, well, wherever it changes concavity, and it's changing at both of them. So at x equals -1, why? Because the second derivative goes from positive to negative, and you are at +1 because the second derivative goes from negative to positive. Ooh, Bella, it's gonna rain. Okay, so we'll pick up with this tomorrow, and I will load this video sometime this afternoon as like a YouTube link. And we'll finish these notes tomorrow and hopefully jump into section 5. Thanks for sticking with me all this time. I hope you guys have a great day today. Let me know if you have any questions, okay? Send me a message.